what this is called is mathematical injection, right? So one way that we can prove conjectures is the principle of mathematical induction, right? And so, whenever I talk about to prove something by the principle of mathematical induction takes 3 steps, okay? So in here, we're proving things that have to do with number theory. So like I said, for example, for all, positive integers, x squared is also a positive integer. Now that's a very basic example, but it's something like that you have to prove. Okay, so the process has 3 steps. The first one is show that something works for the first case, n equals 1. This is called the anchor step, okay? Then assume that it works for any particular case, n equals k. This is the inductive hypothesis. And then show that it works for the case immediately following, n equals k plus 1. That is called the inductive step, okay? So how does that work? So take a look at, let me just show you what I'm talking about. Look at this one. What is this saying? This is saying, look, use mathematical induction to prove that the sum of the first n odd positive integers is n squared. That's a bold statement. The first n positive integers, odd, is n squared. So for example, if I take 1, 3, 5, 7, 9, how many is that? 1, 3, 5, 7, 9, 5. If I add them up, it's going to be 5 squared. And then if I take 1, 3, 5, 7, 9, 11, if I add them up, it's going to be 6 squared, right? That's kind of that's kind of like a weird statement. So how am I going to prove that? So you say, okay, let's see if it works if I'm only talking about one number. And then you're like, okay, that was just pure luck, all right? Let's just pick a random number, okay? Give me a number, a random number. From 15? Okay, let's see if it works for 15 numbers, okay? And then you say, okay, let's just assume that it works for 15. Now that's just a random number we picked, right? So let's assume that it works for 15, and then if it works for the one right after, then mathematically we can say we proved the conjecture.
You prove it 3 times?
You don't need to technically only prove it once. You assume that it works. You assume that it works for one, and then you use that to prove for the other one. All right? So how that works is a little bit beyond the scope of this. It's like proving the proof, but we're going to use it to prove these ones. Okay, so here it says use mathematical induction to prove that the sum of the first n odd positive integers is n squared. That is the statement. In order to make that into a mathematical statement, right, we have to write it with as a mathematical expression. So the first n odd positive integers, okay? So when I started off, that's easy. It's 1, 3, 5. And then how do you come up with the nth term? How do you come up with the nth term? So this is A1, A2, A3. What's AN? AN will be 2n minus 1. Now, in this section, you don't have to come up with AN. It'll be given to you. So like that whole green statement will be given to you. Okay? But do you see how they came up with it? If this is the second term and it's 3, what is it? It's 2 times 2 minus 1. If the third term, 2 times 3 minus 1, that's 5. So like that's how you come up with AN. That's why this is in this chapter. So we have to prove that this is equal to n squared. All right? Exploring here. Right, let's do some exploring here. Suppose n equals 6. What does that look like? I have 6 terms I'm adding. Okay? If you just straight add those, what is that? 3 plus 1, that's 4, plus 5 is 9, 18. What would that be? Is that, how much is it? 36. So how many, this was n equals 6, right? And yeah, that's 6 squared. Okay? Now, let's increase by 1. Let's now go to n equals 7. Okay, the trick is to increase by 1. Now I have 1 plus 3 plus 5, 7, 9, 11, 13. So to 36, now I added 13, so that's going to be 49. How much is that? That's 7 squared. Okay, so what happened? When I had this, when it was n equals 6, this was n squared, correct? Now, when I went to n plus 1, how did my result change? How did I go? If it was n squared, what is it now? 6 squared is n squared, so how would you write 7 squared? N plus 1 squared. This one? So so if I said n equals 6, then this I could write it as n squared. Okay? But now I switch to n plus 1 for 7. So how can I write 49? How can I write 7 squared in terms of n? It's n plus 1 squared. All right? So do you see how it's happening for this one? All right. So now that we've explored this a little bit, let's start our proof. So the first step is show that something works for the first case, n equals 1. So when n equals 1, how does that green step look like? It's 1 on the left-hand side equals 1 squared. Is that a true statement? Yes. Okay, fine. Now you say, number 2, assume that it works for any particular case, n equals k. So now you say, okay, n equals k. For this one, this is the easiest step of all. All you have to do is take the green and switch all the n's to k's. So 1 plus 3 plus 5 plus 2k minus 1 equals k squared. Okay, so all we did is switch n to k. That's all I did here. Okay. Now, I'm going to see if this is going to work for n equals k plus 1. This is the proving step, if you like. This is it. So, okay, on the top here, when I went from 6 to 7, what is it that I changed? I didn't change anything here. I just changed the left side, right? How did I change it? What did I do? I added one more term. I added the next term, okay? So now, here, if this last term is 2k minus 1, what would the next term be? 2k, good. Okay, so let's see how we did that. So it'll be 1 plus 3 plus 5 plus ... plus 2k minus 1. This is what I have, right? Have I changed anything? Have I changed anything? No. Now to this, I'm going to add one more term. The term I'm going to add is 2k plus 1 minus 1. You see what I did? Okay. Now, equals k squared. No, you know what? Let me show it to you like this for a minute. Look at this. Is this the exact same statement from above? Yes? So now, here I'm going to add plus 2k plus 1 minus 1. Okay? Now, is that mathematically legal to just add something to one side?
No.
What do I have to do? Add the same thing to the other side. Okay? Now, okay, so the last term is 2k. Okay, so if n equals k, then it's this. Okay, so if I substitute k, it's this. Now, the next one, I have to substitute k plus 1. Do you remember how we were doing like an, and then the one right before is an minus 1, and then an plus 1? So this is the kth term, and then the k plus 1 term.
Okay.
So k term, and then the k plus 1 term. Okay, you see that? Yeah. Right, because it's 2 times the number minus 1, 2 times the number minus 1, 2 times the next number minus 1. Okay? Now, what did we say before? When I change my, look up here, when I change my n to 1 greater, what does my result look like? N plus 1 squared. Okay? So, if I start with k and go to k plus 1, then I should end with k plus 1 squared. So now the goal is, that's it right there. The goal is simplify right-hand side. By the way, in the physics world, there is an abbreviation, in the math world too, right? We don't write right-hand side, we say RHS. Simplify the right-hand side to look like k plus 1 squared. All right? So,
oh, it's a perfect square.
Yeah, okay, hang on. Don't get ahead of me. Okay, so technically we would write that left-hand side over and over and over and over again, but I'm going to let you not do that. So you have to do like this, so like you have to go linearly, you have to go vertically down with the equal sign aligned. Okay, this is reason for points off. All right, so this is going to be k squared plus 2k plus 2 minus 1. This is k squared plus 2k plus 1. And then can I simplify that? Can I factor that?
Yes.
It's k plus 1 squared. Yeah. So you see that? So now when I have what I want, I put the right-hand side back. So I say 1 plus 3 plus 5 plus ... plus 2k minus 1 plus 2k plus 1 minus 1 is equal to k plus 1 squared. Okay? This is it. We're done. Actually, we shouldn't put that in a box. This is it. We're done. In the end, you can write QED. What is that? QED, that's the symbol for, like, it's basically, it is proven in Latin. And then, or you could, people also do that square, a filled in square. Okay? So, what did we do? When we were off exploring, we discovered that if I add one more term, my right-hand side is going to look like n plus 1 squared. It's not always going to be n plus 1 squared. It's going to be something else. So your objective is, add one more term, see what this is going to look like. Then you're going to do this and make sure you end with what you thought you would end with. Okay? Let's do one more. Huh? Yeah. Use mathematical induction to prove that the sum of the first n positive even integers is n squared plus n. Okay? So the statement, the mathematical statement we have to prove is this. The first n even positive integers, 2, 4, 6, 8, is n squared plus n. Okay? All right. So let's explore. Always do that exploring bit. Okay, pick a number for n. I picked 6 before. Let's do a smaller one. Let's do n equals 4. Okay, so when n equals 4, what does this look like? 2, plus 4 plus 6 plus 8. How much is that? 20. Okay, so it's supposed to be n squared plus n, right? It's supposed to be 4 squared plus 4. Does that work out? Yeah, okay. So now increase your n by 1. So n equals 5. What does my left-hand side look like? Tell me. Uh-huh. 30. Okay, so it's 5 squared plus 5. It does work, right? It's supposed to be n squared plus n. Yeah, okay. So all I do first is, right, just plug it into that formula. Yeah, it's n squared plus n squared plus n. Now my next step, this is the important part, is when I increase n by 1, right, this now became n plus 1. So how can I write this, the 5 squared plus 5, in terms of n? Right, okay? So that looks like n plus 1 squared plus n plus 1. This is probably, if I had to rank three most important things, this is one of them. That step is one of them, all right? So make sure you know how to relate. If this is n squared plus n, then that is n squared plus n plus 1. So now my answer has to look like that. Or, if you like, k plus 1 squared plus k plus 1. That is going to be my end goal, end game, if you like, okay? Haha, yeah. Huh? Uh-huh. Because 4 squared plus, so n was 4, and I had n squared plus n. Now how do I relate that to this? If n is 4, then 5 is n plus 1. So to go from there to there, if that's n squared, then this is n plus 1 squared. If this is n, then this is n plus 1. So basically say, if n is 4, how does 5 relate to n? It's n plus 1. It's 4 plus 1. Right, to the one right above. Okay, now to do this. Okay, so the first one, that's like a Mickey Mouse step, right? N equals 1. You just say 2. Is that the same as n squared plus 1? Is it? Yes, it is. Okay? It's always going to work. Okay. So then you say the n equals k step. And here, there is no thinking involved in that second step. All you do is take the green, but change all the n's to k's. So this is the no thinking involved. I know. So don't mess it up. For the vectors.
Me too.
Okay, so maybe I'll change my terminology. This is the most important step of the whole thing. Okay, so now the thing is, okay, we're assuming it's true for n equals k. Now, how is it going to look for n equals k plus 1? Again, I'll show you how to do this. Here's how I do it, because I'm taking the test and I'm stressed. Oh my gosh, I don't know what's going on. You know what I do? I copy down exactly what I have up there. Have I changed anything other than leaving more space? No, nothing. So now here I'm going to add the next term from this. If I ended with k, the next one is k plus 1. So make all your k's k plus 1s. So it's going to be plus 2 k plus 1. But I can't get away with adding something on one side. I need to add it to the other side, plus 2 k plus 1. Okay? Now that you've done that, leave the LHS, left-hand side, alone. Now you have to massage That's really what it is. The right-hand side to make it look like what you want it to look like. Now, let me give you a little warning. It's not always going to be, you know, all roses like this one, where it naturally works out for you and you have nothing left to do. Oh, no, no, no. Sometimes you have to do some tricks. How do you know what tricks to do? Right now, you don't. I show you a couple of them, and then when you're doing it, you have a couple in your repertoire, and you go, okay, can I try this? Can I try this? Can I try that? You'd have to do a little bit of like magical hand waving, but mathematically legal stuff, okay? Yeah.
So,
Okay, yeah. So k squared plus k plus distribute 2k plus 2, okay? Now the thing is, we have to come up with a k plus 1 squared, right? K plus 1 squared. That means we have to complete the square, like we have to factor somehow, okay? And we just don't have enough numbers to get away with that. What does k plus 1 squared look like in expanded form? That's k squared plus 2k plus 1. Is that right? I have k squared plus 2k, but I don't have a plus 1. So here's the tricky trick that we do, okay? Here's what we're going to do. Okay, I have a 2 here, okay? Can I write it as a 2 or can I write it as a 1 plus 1? Does it really make a difference? How about if I say, you know what, I'm just going to make that 1 plus 1. Because if I ask you how old you are, you can either tell me you're 17 or you could tell me I'm 13 plus 4, right? And that's either a 2 or a 1 plus 1. So now look at what you do. I'm going to group the k squared, the 2k, and one of these 1s. I'm just going to write those together. Plus, what do I have left? A k plus 1. Oh my God, look, I've got the k plus 1. I've got the k plus 1, right? So now I factor this. Look at that. Look at what I have. Do I have what I want it to have? Yes? Look, what did I need in the blue? K plus 1 squared plus k plus 1. And I have it right there. So that's it. I'm done. I copy this back. And there we have it. Done with our proof. Okay? So do you see that? It didn't come out like we had, like, you know, on its own. We had to do a little bit of, like, maneuvering. But it was nothing illegal. Okay? All right, let's do one more. Okay, prove. This is a different one now. So we did 2 where you have like a sequence and it equals something. Now you have 1 where you have a divisibility rule. Prove that 6 to the n minus 1 is divisible by 5 for all positive integers. Oh my gosh, what the heck? Like, how do I do this? Okay, so first of all, divisible by 5. What? Give me some. What are some examples of numbers that are divisible? Okay, so 5, 10, 15. Okay, what else? 35. What do all those have in common? It's 5 times a number, right? 5 times 1, 5 times 3, 5 times 7. So a general form, would that be divisible by 5? That's the form they have, right? It's 5 times n. So that's the sort of number we want. That means it's divisible by 5. All right? So let's do this. N equals 1. 6 to the power of, 1 minus 1. How much does that equal? 5. So does that work? Is that divisible by 5? Yeah, that works. Whew. Okay. N equals k. Now here's the little, here's what you have to do. So for the n equals k step, assume that 6 to the k, remember this is the one where we just changed the n's to k's. Assume 6k minus 1 is divisible by 5. So the way that's going to look is 6 to the k minus 1 is equal to 5 times some number r. We don't want to use k because we're using it. We don't want to use n. That's too close to home. Let's use some other neutral number r. Okay? So that's my k step. Now I need to do the n equals k plus 1. Okay, so remember how we would do exploring before? I kind of left that a little bit because this is a little different. I wanted to wrap our brains around it first. So what should we get? Okay, what should we get? Basically, I have 6k minus 1 here. When I increase to k plus 1, right? When I just change to k plus 1, the result has to be 5 times something. That's what it should look like. All right? So, we're going to start with everything we had. Okay? Now, how do I make the k into a k plus 1? Like here, I just added the next term. It was a sequence. It was different. But here, how do I make the k into a k plus 1? This is a different process. Because it's an exponent, right? The k is in the exponent. You can't just go k plus 1 because you're not adding. What you have to do instead, how do you add 1 to an exponent? That's what you would do. That's what you would do. You multiply both sides by 6. Okay, now this is 6 to the 1, right? Oh, you know what? Hang on. I missed the step. Sorry. Wait. I missed the step. Let's go back. I'm so sorry. I was so anxious about that. Okay, what we want to do first is move the 1 to the other side because I want 6 to the k alone. I don't want to mess things up. Now, like Idan said, we're going to multiply by 6. Okay? So now I have 6 to the k plus 1. Do you see how now in the math I have 6 to the k plus 1? Equals, what do I have? 30r plus 6. But now I kind of went away from the form. What do I want it to look like? 6 to the k minus 1 equals blah, blah, blah. So now let's bring the minus 1 back. Just subtract 1. You can add 1s to both sides, subtract 1s like all day long. It doesn't make a difference. So now I have 6 to the power of k plus 1 minus 1. Look, I already have my left-hand side. Do you see that? Equals 30r plus 5. You can take out a 5. So 6 to the k plus 1 minus 1 is equal to, take out a 5, 6r plus 1. And look at that. That's what I wanted. I wanted 6 to the k plus 1 minus 1 to equal 5 times some stuff. And so now I proved that it's divisible by 5.